rabbit hole. Because at the very beginning of the class, very beginning of the semester, we were talking about a boy raising a flag on a flagpole. And we were talking about how fast that flag was moving, and the goal was that we were looking at some average rates of change. We were looking at average speed or average velocity. And the idea was that we eventually wanted to come up with an instantaneous rate of change, an instantaneous velocity of the flag at a particular time. And in that case, at the time was t equals 2 seconds. Okay. Now, to come up with that, we had to draw a bunch of straight lines. We had average rate of change was the slope of a secant line, but really that included 2 points, and we wanted to make it 1 point, so we ended up having a hole in a graph, and once we had a hole in the graph that we wanted to fill in, then we needed to talk about limits and continuity, and so we went off down this rabbit hole to really get a better grasp of understanding the mathematics of limits. And that entire rabbit hole is our limit idea, but now we can go back to our boy and our flag, okay, with a little bit more solid knowledge of the mathematics that are going on. So I want to remind you about some of the things that we talked about. So recall that we can draw a picture of a function, and we're going to look at the function y is equal to f of x. And the idea was that we wanted to find the slope of a tangent line when x was equal to a. Now, that was challenging because a tangent line is a line that kisses our curve in exactly 1 point, and that doesn't really define a line. To define a line, you need 2 points. And so what we started with is a second point up here, which we'll call that value x. And so the y value for that point is f of x. And the y value for our point A is f of a. And we said that the slope of the secant line between A and x, well, if we wanted to draw that secant line, secant line meaning the line that is going through 2 distinguished points. The slope of the secant line between a and x, well, we would find the difference between the y values and then divide that by the difference in the x values. And so we could write this as f of x minus f of a over x minus a. So our point up here is x comma f of x, and our point down here is a comma f of a. All right, so this was the slope of the secant line, and this was our formula for it. And another way to say this is our average rate of change of our function f. Now, our tangent line, the slope of the tangent line at x is equal to a, so right at this point when x is equal to a, the slope of that tangent line, this is going to be our instantaneous rate of change of f. Now, up until now, we have not really had a way to describe the slope of this tangent line with a formula. But now that we've talked about limits, we can do this. Check this out. Imagine that the whiteboard over there where I've drawn that picture can actually start moving. Okay, and so what we've got going on here is that this secant line. Imagine if I take this point, this x comma f of x, and I move it a little bit closer to my fixed point a comma f of a. I have a new secant line. And if I move it even closer, I get a newer secant line. The closer that I move my x comma f of x point to my a comma f of a point, the closer my secant line looks to looking like the tangent line. In particular, what I'm doing is I'm taking x and I'm moving x as close to a as I can possibly make it go without actually touching a. So in other words, I'm taking a limit as x approaches a. So for the slope of our tangent line, the way that we would write our slope of our tangent line well, I would start out with my slope of my secant line, which is f of x minus f of a, over x minus a. And I want that x point to get as close to a as I possibly can. And so I throw a limit in front. And so this expression, the limit as x approaches a, of f of x minus f of a over x minus a, this expression describes the slope of our tangent line at the point a comma f of a. And in particular, this is our derivative of f at x is equal to a. And notation-wise, I write f prime of a. So it's f of a with a little prime mark up there next to the f. Okay, so this right up here is our limit definition of a derivative. And so I asked you to imagine the board moving, but that's not really, that useful. So I actually want to show you a picture of what this might look like if we were able to have the board